After the Big Bang, the universe was silent, dark, and formless, yet within that chaos lay the ingredients for every planet that would ever exist. Hydrogen and helium spread across expanding space, pulled together by gravity to ignite the first stars. Inside those stars, heavier elements were forged through immense pressure and time, then scattered through violent supernovae. Long before Mars existed, its atoms were already traveling across the cosmos, waiting to assemble. These cosmic explosions seeded clouds of dust and gas, slowly shaping regions where new stars could be born. The story of Mars does not begin with rock or soil, but with light, fire, and the death of ancient suns. Every grain of Martian dust carries the memory of that early universe, linking a cold red planet to the moment everything began. Roughly 4.6 billion years ago, a dense cloud of cosmic debris collapsed under its own gravity, giving birth to our Sun. Around it formed a spinning disk of gas, ice, and dust, where particles collided, merged, and grew over millions of years. Within this chaotic disk, planets were not gently formed, but violently assembled through endless impacts. Mars emerged as one of these early worlds, smaller than Earth, yet shaped by the same brutal forces. Heat from constant collisions melted its interior, while radioactive decay kept its core active. At this stage, Mars was not red or lifeless, but glowing, molten, and unstable, a newborn planet still defining its fate amid the turbulence of a young solar system. As Mars cooled, its surface hardened into a crust, trapping immense heat beneath. Volcanoes erupted across the planet, releasing gases that slowly built an atmosphere. Carbon dioxide, water vapor, and nitrogen thickened the skies, transforming Mars from a barren rock into a world capable of retaining warmth. At the same time, a molten iron core generated a magnetic field, shielding the planet from solar radiation. This invisible barrier allowed the atmosphere to survive, preventing it from being stripped away by the young sun's violent winds. During this period, Mars was not the frozen desert we see today, but a dynamic planet with protection, pressure, and energy, creating conditions that could support liquid water on its surface. With a stable atmosphere in place, Mars entered its most critical phase. Temperatures rose, ice melted, and rain may have fallen across the planet. Rivers carved valleys, lakes filled craters, and possibly even shallow oceans formed in lowlands. Water became a chemical engine, allowing minerals to dissolve, react, and store energy. On Earth, similar environments gave rise to the earliest life. On Mars, the same rules of chemistry applied. Where water persists, complexity follows. The planet now possessed heat, protection, and liquid water, the three fundamental pillars required for habitability. This was Mars at its peak, balanced delicately between chaos and stability, standing at the threshold of something greater. During this window of habitability, Mars may have hosted environments suitable for microbial life. Deep underground, protected from radiation, water could remain liquid for extended periods. Chemical reactions between rock and water may have produced energy sources capable of sustaining simple organisms. If life ever emerged on Mars, it would have been microscopic, resilient, and hidden from view. Yet this opportunity was fragile. Mars was smaller than Earth, and its internal heat was fading. As its core cooled, the magnetic field weakened. Without realizing it, Mars was approaching a turning point where the very systems that once made it alive would begin to fail, setting the stage for a slow planetary death. As Mars continued to cool, its molten core slowly solidified, and the magnetic field that once shielded the planet began to weaken. Without this protection, charged particles from the Sun directly struck the Martian atmosphere, stripping it away molecule by molecule. Over millions of years, air pressure dropped, temperatures fell, and surface water became unstable. Rivers dried, lakes evaporated, and oceans either froze or escaped into space. This was not a sudden catastrophe, but a gradual unraveling. Mars did not die in a single moment. It faded. The planet crossed an invisible line where recovery was no longer possible, transforming from a potentially living world into one increasingly hostile to life as we understand it. With the atmosphere thinning radiation reached the surface in levels far beyond what complex biology could tolerate. Any life that may have existed was forced to retreat underground, where rock could provide shielding and water might still persist. Mars became a planet of refuges rather than abundance. Chemical energy, not sunlight, would have been the only viable power source for survival. Similar ecosystems exist on Earth today, hidden deep beneath oceans and continents. On Mars, these environments may have represented the last strongholds of life. Yet even these sanctuaries were temporary. As water reservoirs shrank and geothermal energy declined, the window for biological activity narrowed further, pushing Mars closer to permanent dormancy. By around 3 billion years ago, Mars had largely lost its surface habitability. Ice dominated the poles, while dust storms reshaped the barren terrain. What once flowed now lay frozen or locked within minerals. The sky thinned into the pale haze seen today, incapable of trapping warmth. Despite this decline, Mars preserved its history remarkably well. Unlike Earth, which constantly renews its surface, Mars became a geological archive. Ancient riverbeds, delta formations, and mineral deposits remained exposed, silently recording a time when water shaped the land. These preserved features act as time capsules, offering scientists direct evidence that Mars was once profoundly different from the lifeless world we observe now. In recent decades, robotic explorers have begun decoding this ancient record. Rovers have discovered clay minerals, organic compounds, and chemical signatures that form only in the presence of water. Seasonal methane releases hint at ongoing processes beneath the surface, though their origin remains uncertain. Methane can be produced by geological reactions, but on Earth, it is also strongly associated with life. This ambiguity keeps the question alive. Mars continues to challenge our definitions of life and habitability. It is no longer a living planet, yet it may not be entirely dead. Beneath its frozen exterior, remnants of its active past could still linger, waiting to be understood. The story of Mars is more than a tale of planetary failure. It is a warning written in stone. Mars shows how delicate habitability truly is, and how closely life depends on planetary balance. Small differences in size, magnetic strength, and internal heat can determine whether a world thrives or collapses. By studying Mars, we are indirectly studying Earth's future and the limits of life in the universe. Mars reminds us that being alive is not permanent, even for planets. It stands as a silent monument to what can happen when protection fades and time runs out, urging humanity to understand not only where life begins, but how it survives. Today, Mars appears quiet and motionless, yet it remains one of the most scientifically active planets we study. Beneath its surface, radar scans reveal vast reservoirs of frozen water, layered like pages of a forgotten book. In some regions, salts lower the freezing point, allowing briny liquid water to briefly exist even now. These environments are harsh, but not impossible for life. On Earth, microorganisms survive in similar extremes, feeding on chemical reactions rather than sunlight. If life ever took hold on Mars, these subsurface zones may still preserve traces of it. Mars is no longer a cradle of life, but it may still be a vault, protecting secrets from a warmer era. The search for life on Mars is also a search for ourselves. Every rover, lander, and satellite sent to the planet is guided by a simple question: are we alone? By analyzing Martian soil and atmosphere, scientists hope to understand whether life emerges easily when conditions allow, or if Earth is a rare exception. If Mars once hosted life, even briefly, it would suggest that biology is a natural outcome of planetary evolution. If not, it would imply that life requires an even more precise balance than previously believed. Either answer reshapes our understanding of the universe and our place within it, making Mars one of the most important worlds ever explored. Mars also serves as a mirror, reflecting Earth's vulnerability. Our planet still has a strong magnetic field, active geology, and abundant water, but these systems are not guaranteed forever. Mars shows that planetary protection can fade, and when it does, recovery may be impossible. Climate stability is not permanent, and habitability is not a fixed state. By studying how Mars lost its atmosphere and water, scientists gain insight into long-term planetary survival. The lessons learned are not abstract. They directly inform how humanity understands climate, sustainability, and the fragile systems that keep Earth alive today. Future missions aim to return samples from Mars, allowing scientists to study its history with unprecedented precision. Within these rocks may lie chemical fingerprints of ancient water or even fossilized traces of microbial life. Such discoveries would not only confirm Mars's living past, but redefine life as a cosmic phenomenon rather than a terrestrial accident. Even if no life is found, the absence itself would be profound, forcing us to rethink how rare life truly is. Mars has become a testing ground for humanity's greatest questions, bridging astronomy, biology, and philosophy into a single red horizon. Mars after the Big Bang was not destined to fail. For a time, it had everything needed to live: warmth, water, energy, and protection aligned, opening a brief window of possibility. That window closed, not through disaster, but through slow planetary aging. The rise and fall of Mars reveals that life depends not only on beginnings, but on endurance. As we look toward other worlds and distant stars, Mars stands as both inspiration and caution. It tells us that life may be common, but survival is rare. In the silence of the red planet, the universe asks a final question: how long can any world remain alive?